We now introduce one of the most important concepts in classical probability, and it is the concept of conditional probability. Now, up to this point, the questions that we've dealt with as far as probability is concerned, um, these were questions that answered like, okay, here's an experiment, and we define a particular event, and then we want to know what is the probability that that event occurs. Or we define two events, and then we might ask the question, what is the probability that they both occur, right? So no prior information is known. All we know is we've defined the experiment, we've defined these events, and then we're computing their likelihood, right? Well, in conditional probability, you tend to know a little bit more information. So now the question is this. Suppose we know that event B has occurred. That's a given. How does that affect the probability of some other event, let's say A, right? And that's what conditional probability is. We now know a little bit more information, and we want to know how does that affect the likelihood of some other event, right? So let's introduce the notation first, right? That's the concept behind it, and how do we write this down? So the probability that event A occurs given that event B has occurred, right? And that's the new part, right? Is written, or just say is denoted, and is denoted by this. So P for probability, A, but now we're going to put a little bit more here that's going to give us the idea that B has occurred, and it's this notation, right? So this is read the probability of A given B. So what's inside the parentheses is read A given B, right? So knowing that B has occurred, I want to know how does that affect the likelihood of A occurring? Does it make it more likely, less likely, or does it not affect it at all, right? In fact, that third scenario where B, the occurrence of B does not affect the likelihood of the occurrence of A, that's a huge concept which is again just down the road. So we're really building some good stuff here, right? Now it turns out there's a very simple formula for this. In fact, it's just the way it's defined. But what I'm going to do is kind of give you an example as to why the conditional probability is defined the way it is. So I'm going to use an example to kind of motivate the idea behind the definition. All right. So let's consider a Venn diagram, and I'm going to have to draw this one pretty big, right? So it's going to have to be a big Venn diagram because I'm going to put a lot more information on it than I normally do in a Venn diagram. In other words, I'm going to put a bit more detail on our or in our Venn diagram. All right, so still just this is still a two event case, right? But instead of just saying, okay, just kind of lumping it all together and say event B has this one probability associated with it, I'm actually going to break it down to the specific outcomes that are in B, and then the specific outcomes that are in A and where they overlap, and the specific outcomes that are outside of both A and B. So what I'll do, I'll indicate those specific outcomes, right? And remember, an outcome is just one possibility of the experiment, the way the experiment ends. So let's say and what I'll do is label each of these specific outcomes with their probability. So this one is going to have probability 0.04. This one will have a probability 0.14. And then this one down here, probability 0.12, right? So in other words, these are the three outcomes, or sometimes they're called simple events, meaning just one um, uh, specific outcome. These are the three simple events that would lead to only B occurring, right? So these three are only in the B region. Now, where they A and B overlap, they're going to have two simple events in common. One will have probability 0.07, and then the other one with probability 0. Oh, that doesn't look like a point. So 0.19, and then A alone just has one simple event and a pretty low probability of 0.01. And then we have three now that are outside of both circles. And we know there has to be more, because if I add up these numbers, I still don't get my total probability of 1. So the remaining probabilities are, so here's one over here with probability 0.22. Here's one right here with probability 0.03. And then here is one over here with probability 0.1, that would be 1/8, right? So that one. All right, so there we go. So again, the red dots, let me just make my little key over here. These are just specific outcomes, or sometimes called simple events of our experiment, right? Now, so we could look at this and we could write certain things down. We could go and total up A. So we could say, for instance, that the probability of A, well, there are three simple events that would lead to event A occurring, and those total up. So we got 0.01 plus 0.19, so that's 0.2, and then so for a total of 0.27. So A, again, with no prior knowledge, right, or nothing else happening, A has a 20% chance of occurring. Let's do the same for B. So the probability of B, we have a few more to add up. So add these two, you get 0.26. Add this one to it, you get 0.3, and then 0.44, and then 0.56. So 0.56. Let's just look at the intersection. Again, these are like the three standard things that you typically start out almost any of these more just kind of theoretical problems with. And then so the probability of A intersect B. So just add up the probabilities of the two outcomes in the intersection, and that's where we'll get our 0.26, right? Okay. Good. So these are, again, the familiar types of probabilities that we've computed. So now here's the question. Suppose we know that B has occurred, right? In fact, let me scoot this over a little bit more. So if B has occurred, how does that change the likelihood that A will occur? So if B has occurred, how is the event A affected, right? So how does this occurrence, knowing that B has occurred, how does that affect A? Well, if B has occurred, then suddenly it's almost like this becomes the new sample space, right? It's like that becomes the new sample space. Because if B has occurred, then it would have to be one of these five outcomes, right? One of these would have to have occurred for us to say that B has occurred. So it's almost like we're saying, because B has occurred, we can throw out everything outside the circle here that I have highlighted in blue or redrawn in blue. So basically, again, I'll just say that so given B, right, this now becomes, and I'll put it in quotes, it's not really a formal way of saying it, but really this is now my new sample space. Right? It can't be any of the other ones, right? It has to be the ones inside the blue circle. Excuse me. So then, if we now want to know of all of these five, right? Because we still don't know which of the five. We just know that it's one of them, right? How many ways, or in how many ways can A also occur, right? Because so that's what we're saying. Given that it's one of these five, we want to know what is the probability that A will occur. Well, A will occur if it's right here, right? Again, so look at what we have. It's like we've shrunken our sample space down to B, and then because we know we have to be inside of B, then we have like tossed this possibility out. And then if we were to apply our classical probability approach, right? I'm not even going to write, I'm just going to say, so listen carefully. If we're supposed to apply uh, our classical probability approach to now update the likelihood of A occurring, we would have to take essentially the sum of what's in the blue circle. That would become my denominator, right? And we would have to divide that by the sum of what's in the green circle. That would be my numerator, right? So it's like, so what would happen is, and let me just scroll a little bit more over here so I can write it down. So now let's see, if we want to find the probability of A given B, and what I'll use is, let's use the N notation. So based on what I'm saying, if we were to find essentially the probability of A intersect B, so that's what's in the green, and then divide it by what's in the blue, well, the entire blue, that's just the probability of B, right? Because now the probability of B essentially represents the probability of my new sample space, right? And this is actually our definition for the conditional probability. So I can write it down, right? Based on the values that we just computed, these two, I can write down what the probability of A given B is. So if I take the probability of the intersection, so 0.26, and divide it by the probability of B, which is the 0.56, then that gives us the probability of 0.464. And now look at so if we compare it to our previous probability of A, you can see the likelihood not quite doubled, but is certainly increased significantly. So the probability that A occurs with nothing else, with again no prior information, that's 0.27. The probability that A will occur, given that we know B has occurred, then it's now 0.464, right? So let's write down a couple things here. I'll just give you some terminology as well. So when you have something like the probability of A with no prior information, right? It's just the probability of A. This is sometimes called a prior probability. When we update this probabilities now to say, okay, now I know something a little bit more. I know that B has occurred, and we computed this to be 0.464. This is now called a posterior probability. After the fact, hence post, right? So posterior probability, right? And so with this added information, we can then improve our measure of the likelihood of A. Now, it's not that this is bad. This is just saying that now we've added a bit more to the information. So knowing a little bit more, we then update this and we get a posterior probability, right? So now this idea is the motivation for our definition. So let's actually write it down. That way you have it. All right, so the conditional probability of event A and sometimes we say conditional on B. So on event B is defined as, all right, so let's use our notation. So it's defined as the probability of A given B. That's the notation, and the definition is the probability of A and B, that's the intersection, right, divided by the probability of B. And the assumption here is that since we don't want to divide by 0, and we know we can't have negative probabilities, so then that only leaves us with a positive value in the denominator, right? And that's the definition. So I wanted you to see where the definition comes from, in the sense that this given idea is essentially updating what we would put in the denominator, right? So it's not the entire sample space now, it's just the essentially the measure of B, right? The measure of B's likelihood is what goes in the denominator, and then what goes in the numerator is the measure of likelihood of A and B occurring, right? And again, so let's just have this formally stated. What does it measure? It measures the probability of event A occurring when it is known that B has occurred, right? So, and that's key, when it is known that event B has occurred, right? And that's it. So let's do another example. And what I'll do with this example is simply walk through some of the different ways the question can be set up, and we can see how the posterior probabilities compare with the prior probabilities and so forth, right? Again, do they always go up? Do they go down? Well, it depends. It depends on this ratio right here, right? So let's look at an example. And let's say, so given that the probability of A is 0.3 and the probability of B is 0.45, and the probability, let's say we know the probability of the union, so the probability of the union is 0.85, right? Let's first draw the Venn diagram for this so we can see the Venn diagram, and then I'll just walk through different things that can be asked, right? So let's see what we have here. As far as on the Venn diagram, we have, so we know what goes in, again, in total, what's in A, what's in B, and then what's in A and or B, so our inclusive or. What we don't really know right now is what's just in the intersection, right? But remember, what we have is we have this particular formula. Oh, actually, I think let me fix a number here. So this will be, actually, no. That number is correct. This number is not. Oh, come on. There we go. Yeah, so that is 0.6. Okay, there we go. So first, let's find the probability of the intersection. So we can do this off to the side. We can use our general addition rule. The probability of the union is equal to the probability of A plus the probability of B minus the probability of the intersection, right? So let's plug in the three values that we know. So we have a 0.6 there, and then we have a 0.3 there, and then plus a 0.45, and then the quantity that we don't know is the probability of the intersection. So let's see. So we have 0.6, and then over here we have 0.75, and then minus the probability of the intersection. So, you know, there are different ways you could do it. We can add the probability of the intersection of A and B to both sides and then subtract 0.6 from both sides. So we will end up with this. So the probability of A intersect B is 0.75 minus 0.6, and then that gives us 0.15. All right, so now let's go ahead and label our Venn diagram. If we can get our Venn diagram completely labeled, again, even if we throw these conditional probabilities into the mix, the Venn diagram will still give us all the information we need, and we simply have to apply the definition that we just wrote down, right? So let's put the 0.15 in the overlapping region and then work our way out using the fact that, for instance, all of A must sum to a probability of 0.3. So we have 0.15 already here, so we have to have the remaining 0.15 out there, right? And then let's see, all of B must sum to 0.45, and we have 0.15 already accounted for in the intersection, so that leaves a 0.3 outside. I'm sorry, outside of the intersection, but inside of B. And then, so in total, there's our union. See, it still adds up to the 0.6. So everything inside all the circles sum to 0.6. So that means there is a 0.4 outside the circles, but inside our sample space, right? Okay, good. So we have that figured out. So let's go through and just compute some conditional probabilities. And what I will do is I will set up the ratio, and you can simplify the numbers. Again, the arithmetic is the almost trivial part of these. It's making sure that you're interpreting the problem correctly and then applying the appropriate formula. So let's look at part A. Let's say we want to find the probability of A given B, right? So that's the probability of A intersect B over the probability of B. And we have all that now, right? We have that, based on what I wrote down here and what we filled in on the Venn diagram, we have exactly what we need. So the probability of the intersection is 0.15. The probability of B is 0.45, and then you could simplify. It looks like that comes out to be 1/3, right? Yeah, in fact, I'll write it down. Looks like 1/3, right? And so you can see, so this, if you compare this posterior probability with the prior probability of 0.3, you can see that this is just slightly bigger. Right? So this one is a slight increase, not quite as dramatic as we saw earlier, but it's still more likely for A to occur given that B has occurred, as opposed to A just occurring in this prior non-conditional way, if you want to use that phrase, right? Okay, so let's look at what if we flip it around? What if we take the probability of B given A? Now what happens is, and the reason why I want you to see this is there are a couple properties of the set operation that will come into play, but it's not going to be the same as the probability of B given A, because in general the denominators might be different, right? Because if we write it down, by definition, this is the probability of B intersect A, and we now have to divide by the probability of A. But remember, B intersect A is the same as A intersect B. So this numerator, right, is the same as this numerator, but here we have a different denominator, right? So it's not going to work out to be the same, right? So basically, the conditional probabilities are not commutative. I can't switch the events and expect the result to be the same, right? It might be, and that might depend on if the probability of A and B are the same, right? And which certainly could happen, but in this case it doesn't. So it's not a general principle here. So you have your 0.5 in the numerator, 0.15 in the numerator, and then you have 0.3 in the denominator, and this simplifies to 1/2, right? And remember, the probability of B, let me write them over here again. So the probability of A, that is 0.3, and that one increased. The probability of B, that was 0.45, and then that one has increased, right? So again, with this added information, we can see the effect that it's having on these particular probabilities. Now, what if we were to throw like a complement in there, right? So what if we wanted, for instance, to find the probability of A complement given B, right? Well, again, let's write down the definition. So this will be the probability of A complement intersect B divided by the probability of B. Well, let's see, the probability of not A and B, well, we can get that from the Venn diagram. Not A means I'm outside of circle A, and I'm inside circle B. So that would be 0.3, right? So this is going to be 0.3, and then we have to divide that by the probability of B, which is our 0.45, right? And this reduces to 2/3. And it is not a coincidence that the probability of A given B and the probability of A complement given B, it's not a coincidence that these two add up to 1, right? In fact, that is a property that can be proven if we simply use the definitions of our set operations and of the conditional probability. I would leave that for you to try to think about it. But I'll put it as a note over here. And what I will do, I will write down our original complement rule and show you how it is modified now in the context of conditional probability. So remember, we know that the probability of an event plus the probability of its complement must add up to 1. Either the event occurs or it does not, right? Well, if I now update it and say B has occurred, well, this is also true. The probability of A given B plus the probability of A complement given B, that also has to be equal to 1. Because given that something else has occurred, either A is also going to occur or it is not going to occur. So what's nice about this is our complement rule, right, or complementary rule, carries over even in the presence of conditioning, right? But what we can't say is there is no, and I'll write this one in red because this is one that sometimes gets confused. There is no general relationship, or let's say rule, relating these two. If I write down the probability of A given B and the probability of A given B complement. So unfortunately, there is no general rule that we could say that, okay, this always happens for these two. We just can't say it. But what we can say is if we condition on the same event, in this case up here B, then the probability of A given B plus the probability of A complement given B must be equal to 1. All right? Let's do one more example before we wrap this up. And our last one, let's take what if we have something like the probability of A complement given B complement, right? So the way this would be read, we're measuring the likelihood that A will not occur given that B did not occur, right? Well, again, you can reason it out in your mind by adjusting the sample space like we did earlier, but often I think the best approach is just to use that simple definition. So we're going to write this down as the probability of not A and not B divided by the probability of not B. Right? Okay, so let me scroll back up so we can see the Venn diagram. Not A and not B means you're outside of both circles. Hence, that probability is 0.4. Right? So this is 0.4. The probability of not B, well, that's 1 minus the probability of B. There's our complement rule again. And the probability of B in this example is 0.45. So we got 0.4 divided by 1 minus 0.45 is 0.55. And let's see, that reduces to 8/11. Yes, so that's our probability. So the likelihood that A will not occur given that B has not occurred is 8/11, right? So with the definition, this is probably one of the simplest definitions that we have. Hopefully you followed along through the motivation for how, why do we use this fraction as a measure of the likelihood of this, this conditional event thing. And then we can see that once you have the Venn diagram, all the information that you need is there, provided you set up our correct quotient. All right. So we'll stop there, and we'll see you in the next video.